Welcome back, folks. Today we will be discussing about adjacency list. In our last video, we discussed about adjacency matrix. Just to add, this is an excerpt from a live session I had for GDSC Banasthali University.
All right. So let's talk about how do we represent a graph. So a graph can be represented in four ways. The four ways which I know of. There can be more ways. First is adjacency matrix, adjacency list, a generic graph which say we want to make it entirely object oriented, and we want to put our other two representations on steroids and create something entirely different, encapsulated and whatnot. The next is adjacency set or disjoint sets. This is another way to represent graphs, and you would find these graphs and you would find these concepts in when you would have a bunch of graphs who have a cyclic nature, and then there is another bunch which has again a cycle. So you bunch them into a single graph and use disjoint sets there and use union on that. So this is out of syllabus for now, all right, because I haven't prepared it. So, but for sparsely connected graphs, what we have is an adjacency list. What is an adjacency list? Now, this is interesting. What we do here is we have a list, right? Or let's say we have an array of our vertices. And every element in our array is a linked list, right? So this is a linked list inside this. This is a linked list. This is a linked list. This is a linked list. All right. How do we actually represent it? Let's see. So we are keeping a track of all our vertices just to keep their indices, and we are keeping array of linked lists. Array of linked lists. This is how we read it. Array of linked lists. All right. So now we have to create our adjacent list graph. Again, we'll have to provide a vertex count. And we provide a vertex count. We initialize our vertices. We initialize our edges. Right? We initialize our edges with the vertex count because it's an array. Now what we do is we add our indices, and in those indices we create our linked lists. All right. So now we know that where can we find our linked lists. Oops. So when we have to add an edge, what we do is from the vertices where we are indexing our nodes, indexing our array lists, we get the index, our source index, our target index, right? We create a source node and a target node. We have to make sure that while we are adding our edge, we are not adding it to a place which doesn't exist at all. So this is check here which we do, and then what we do is we set the value of our source and target, right? And at that particular index, what we do is we insert add head. Right? Say we had A, B, C, D. We had to add an edge from A to B. So let's say we had to add an edge from A to C. We added A to C. But then now we had to add an edge from A to B. So we add B at the head, at the beginning, basically. Now, it is very important to keep a track of the time and space complexities while we are solving graph questions. And it is very important to remind ourselves, and it's very important to know that how these data structures and how these representations affect reads and writes and space. So here's the table. I mostly refer this table. This table is basically from Karumanchi, and it is really good. And it's better to, if if we can keep a note of this table while we are solving questions, and keep a mental map of it. It helps. Certainly, it helps.
Alright folks, that's it for today. In the next video, we'll be discussing about how to represent a graph in a more abstract way. Thank you.